Lesson number 2, geometric series. There are two types of geometric series, and these are finite geometric series and infinite geometric series. So, in this video, I'm going to discuss the second type of geometric series, and that is the infinite geometric series. It is actually the sum of the terms of a geometric sequence that continues indefinitely, meaning we cannot identify the number of terms. So there is no number of terms involved, or there is no small letter n, which is the symbol for that number of terms. It may or may not have a finite sum depending on the common ratio or the value of the common ratio. Can be written as S equals A plus AR plus AR squared plus AR cubed plus AI 4, and so on and so forth without end, where A denotes the first term and R denotes the common ratio. Now, when do we say that the sum of this infinite geometric series exists? Now, the sum exists if the absolute value of the common ratio R is less than 1, which means R is greater than -1 but less than +1. Thus, this sequence converges. So meaning to say, the terms of this sequence are decreasing as the sequence approaches 0, or each succeeding terms approaches 0. That is what we meant by the converging sequence. Now, its sum will not approach the finite value, and this sequence is said to be diverging, meaning the absolute value of the common ratio, or R, is greater than or equal to 1. When we say diverge, it is the opposite meaning of converge. So that is R is less than or equal to -1, or the same R is greater than or equal to 1. Hence, the terms gets larger and larger, or oscillate without settling. Now, for the formula for the sum of the infinite geometric series is S equals A over the quantity 1 minus R. So there is no number of terms involved because this is infinite geometric series. So S is the infinite sum, or the finite sum rather, provided that the common ratio, or the absolute value of the common ratio R, is less than 1. A is the first term and R is the common ratio. Now let us proceed immediately to some examples. Let us take the first one. Find the sum if it exists in the geometric series 8 plus 4 plus 2 plus 1 plus 1/2, and so on and so forth. So what do we need here? A, which is 8, and R, which is equal to 4 divided by 8, or pwedeng 2 divided by 4, or 1 divided by 2, which is simply 1/2. Now we try to verify first the obtained value of R, which is at this point 1/2. And you will notice that 1/2 is less than 1. Therefore, we could say that the series converges and there is a finite sum. So the sum really exists. Therefore, we can now proceed to compute for the sum, which is denoted by S. And that is S equals A over the quantity 1 minus R. Substituting the given value, so S is equal to 8 over the quantity 1 minus 1/2. 1 can be changed to 2 over 2, so that 2 over 2 would be similar to 1/2. So we have 8 all over the quantity 2 over 2 minus 1/2 also. So the denominator becomes 1/2. So it's simply 8 over 1/2. Simplifying the expression further, that is simply 8 times 2, and the answer is 16. Okay? Next. Example number 2. Find the sum if its value exists in this geometric series. 3 minus 1 plus 1/3 minus 1 over 9 plus, and so on and so forth. So what are the things that we need to compute for the sum? Of course, we need the first term, which is A, and that is 3, and R, which is the common ratio. And we can find the value by dividing -1 by 3. Or we can consider dividing +1/3 by -1. The result for the value of R is still the same, which is -1/3. And if we're going to consider finding the absolute value of -1/3, that is simply 1/3. And we know that 1/3 is also less than 1. Therefore, just like in example number 1, this series converges and the sum exists. There is a finite sum. So we can now proceed to compute for the value of S, or sum. Using the same formula, S equals A over the quantity 1 minus R. Substituting the value, so that is 3 all over quantity 1 minus -1/3. And we know that 1 minus -1/3 becomes 1 plus 1/3. And 1 can be replaced by 3 over 3, making it similar to 1/3. And 3 over 3 plus 1/3 is 4 over 3. So simplifying the expression further, that is 3 over 4 over 3. We reciprocate the value of the denominator and multiply that by 3. So your S will simply 3 times 3 over 4, and the answer is 9 over 4. Okay. So this is the sum of this geometric series, infinite geometric series. Next, example number 3. Find the sum if it exists in the geometric series. 1 plus 2 plus 4 plus 8, and so on and so forth. A is 1, and the common ratio is 4 over 2, 2 over 1, or 8 over 4. And the result is 2. And you will notice again, 2 is this time greater than 1. Therefore, the series diverges and it does not have a finite sum. Okay? Because it is no longer less than 1, but 2. And if we try to add these first 4 terms partially, the sum is what? 15. Now, if we try to compute for the value of S using the formula, what value what will be the value? Let us check. So S equals A over the quantity 1 minus R, which is our formula. We substitute. Yun. Okay, 1 over the quantity 1 minus 2. And you know that 1 minus 2 is negative 1. So 1 divided by negative 1 is equal to negative 1. If we're going to compare this value for the partial sum, it follows that negative 1 is way off to the actual value of 15, which is the partial sum. So meaning to say, the value is what? Meaningless. Okay?